Okay, good morning, everybody. Hope you're all doing well. So midterms. The midterms are graded. I've got them here. The plan is to stop a few minutes early to give you some time to pick them up. So we'll do that at the end of the class. I've got up on the screen the distribution of grades, and so you can see the average was 62%. And the distribution is a little bit skewed towards the higher end of the scale, so that's good. 23% or almost a quarter of the students got 80% or better. So if you haven't seen it, I just posted the marks late last night. So they're on Canvas, and I also this morning posted my solutions to the course website, so you can take a look at them there. When I return the midterms, what you may find is that some marks are scratched out and changed. That's because what we did initially is the TAs did the grading, and then I went through every question and just made some adjustments if I thought they were necessary. Those adjustments were always like small increases to the grade. So when you get your midterm back, you can compare your answers to the solutions. And if you have any issues, feel free to come see me in office hours. However, I will say I have looked at every single paper, every single question. So it's unlikely that I will change your grade unless there's like some obvious mistake, like they were added up incorrectly or something like that. Okay, good. So what, oh, I see. And then the other things to just remind you of, we have, as usual, our homework due on Friday. You're going to do lab number 5 this week. There is no pre-lab for lab number 5. And then also tutorials, if you're registered in one of the tutorials, they will resume this week. Okay, so in lab 5, and in fact in lab 6 as well, we're going to be talking about RC circuits. So a circuit that involves some kind of resistor and capacitor. In lab number 5, it'll be the hydraulic and analog. And then when you get to lab number 6 next week, it will be like an electronic version of an RC type circuit. So what I want to do is I want to continue the discussion that we started last time, where we imagined that we had a circuit that was a battery, a switch, a resistor, and a capacitor. So what we're going to do is we're going to assume that the capacitor is initially uncharged. Then we're going to close the switch. When we close the switch, the battery drives a current, which will start to charge the capacitor. We applied the Kirchhoff voltage loop rule around the circuit. So we started in the bottom left corner, and we went clockwise around the circuit and just keep track of all the changes in voltages as we go around. So the first thing that happens is we gain the voltage of the battery. So that's plus delta V. Then we cross the resistor. When we cross the resistor, we lose the potential of I times R. And then when we cross the capacitor, we go from the positive to the negative plate. So again, we lose potential in that case. And so we go minus the voltage across the capacitor, which is Q divided by C. And so that's what led to this expression right here. And I'm going to call that equation 0, and we're going to come back to it. Okay, so what we're going to do is we're going to solve equation 0 for the current I. All right, so all we'll do is we'll rearrange things. So we'll take the minus IR over to the right-hand side. So it becomes a plus IR on the right. And then to isolate the current, we just divide by the resistance R. And if we did that, we would get I is equal to, let's see, delta V divided by R minus Q over R times C. Okay. Delta V is the battery voltage. R is just the value of our resistor. To avoid having to write down that ratio all of the time, I'm just going to define this thing to be I naught. Okay, so instead of writing down two constants, we'll just write down that one. I naught has a physical interpretation. Remember, we talked about this last time. So initially, if the capacitor is uncharged, Q is equal to 0, the voltage across the capacitor, which is given by Q divided by C. Sorry, that's wrong. The voltage, let's see. C is defined to be Q over delta V. Oh yeah, that was right. So the voltage across the capacitor is Q divided by C. So if Q is 0, initially there's no voltage across the capacitor, and that means delta V minus IR has to be 0. And so that's the initial current is the battery voltage divided by R. So what this I naught represents is the current at T equals 0 when the switch is closed and the capacitor voltage is 0. Okay, so that's the physical meaning of I naught. I'm going to define one more constant for convenience. The other term on the right-hand side is Q divided by RC. R times C is just a constant. Instead of writing that product over and over again, what we'll do is we'll define RC to be the Greek letter tau. So I'm using tau because that's what you'll see it written as everywhere you look, if you look online or read a book. And so this is tau. It also has a physical interpretation. What we're going to find is that tau is going to be the characteristic time that it takes the capacitor to charge up to some value. And so this is called a time constant. So it's often called the RC time constant because it's determined by the product of R times C. Okay, so with those definitions, I'll just write it down here so it's a little more clear. We're going to define I naught is the battery voltage divided by R, and tau is R times C. Okay, so therefore, the current at any time in our RC circuit is given by, well, all we're going to do is rewrite this expression at the top of the screen just in terms of our new constants. So I will be equal to I naught, which is the current at T equals 0, minus Q over tau. And I'll call this equation 1. I think the first one we labeled 0, so we'll call this one equation 1. This is consistent with the discussion that we had last time on Friday, where we said, you know, once I close the switch, we initially have a large current. That current starts to deposit charge on our capacitor. As the capacitor acquires charge, the voltage across it goes up. That means the voltage across the resistor must go down because of the loop rule. If the voltage across the resistor goes down, that's equal to I times R. R is a constant, so the current must be going down. And you could see that that must be the case because we have I naught, the initial current, and then minus something. And so the more charge that our capacitor accumulates, the smaller the current in our circuit gets. Eventually, our capacitor will reach some maximum charge, and at that time, the current in our circuit will go to 0. Okay, the current would have to go to 0 when the capacitor is fully charged, because if it was not 0, then that current would keep adding more charge to our capacitor, and therefore it wouldn't have its maximum charge. Okay, so what we're going to do is we're going to say, since I is delta Q over delta T. Remember, the definition of current was if we had like a conducting wire and we put an imaginary surface through that wire, if we count how much charge crosses that surface, delta Q in a time delta T, the ratio of those two defines the current. So if I is delta Q over delta T, then we could use that to actually calculate the change in charge on our capacitor. So we can calculate how much charge is added to the capacitor in time delta T using, well, all I'm going to do is I'm going to solve delta Q over delta T equals I. I'm going to solve that for delta Q. And so delta Q would be equal to I times delta T. Okay, and this will be equation 2. All right, so here's the strategy. We'll write it down in a second. What we're going to do is we're going to imagine that we start with our capacitor uncharged and then we close the switch. That's time t equals 0 and Q is equal to 0 at that time. What we'll do is we'll then use equation 1 to calculate the current. For that initial step, Q will be equal to 0, and so the current will just be equal to I naught. Then we'll say we'll pick some time interval, whatever you want. Maybe it's 1 second or something like that. Then we take that current, say it's I naught for the first step. We multiply it by our delta T. That gives us a new charge. Then that gives us how much charge was added to the capacitor. Then what we'll do is we'll say, okay, now we know that the charge is the initial charge plus the delta Q, and the time is going to go from the initial time plus delta T. Then we go back to equation 1. We calculate the current again. We update the current. This time it won't be I naught because we have some non-zero charge on our capacitor. Okay, we take that updated current, we calculate how much charge is added to the capacitor. This time we'll use the same time interval delta T, but the amount of charge we'll add will be a little bit less because now the current is a little bit smaller. Okay, and then you say, okay, I'll take that delta Q, add it to the charge that was there at the beginning of the step. I'll advance my time by another step delta T, and I'll just keep going back. So we'll just keep going back to equation 1, equation 2, feed back into equation 1, back to equation 2, and we just keep iterating over these two calculations. And eventually we'll find that we're going to reach some stable value of the charge where the capacitor is no longer acquiring more charge. The current is essentially 0. And we'll show you a demonstration of that. Okay, so after finding delta Q, we know that the new charge on the capacitor is the original value of Q plus delta Q. So in other words, Q will be updated from whatever value it was to that value plus the change in the charge. Likewise, we'll say that our time goes from the original time to whatever delta T, whatever step size we chose. Okay, so what I'm going to do is I'm going to write out the strategy in full, and then we'll show you an implementation of that strategy. Okay, so strategy. Okay, so we're going to start with known values of the battery voltage, the resistance, and the capacitance. So you assemble some circuit, you have to make some choices about what components you're going to use. Maybe it's a 9-volt battery, a 1 kilo ohm resistor, and a 1 microfarad capacitor or something. You just have to make some choices. These are all constants. They're not going to change through this entire process. Okay, then we're going to pick a value for our time interval, delta t. And we're also going to calculate I naught is the battery voltage divided by R, and tau is equal to RC. And the delta t and these I naught and tau, they're also constants. They're also, those values will never change during this entire process. Okay, so now we start to do the calculation. So we're going to start with Q equals 0 at T equals 0. Okay, and so the first step is to go to equation 1 and calculate the current. So we're going to use equation 1 to find the current. Okay, that's easy enough. It's just I naught minus Q over tau. Okay, and then Q is 0 for this first step. Then we're going to use equation 2. So let me just show you equation 2. Equation 2 tells us how much the charge on the capacitor changes during time delta t. So we're going to use equation 2 to find delta Q, and that's the change in the capacitor charge during time interval delta t. Okay. So now we know how much the charge on the capacitor has changed, so we can update the value of Q. So we're going to update the value of Q, and all we have to do is we take the initial, we take the initial charge and add to it the change in the charge, delta Q. All right, likewise, we update the time. So update the current time is potentially confusing. Let's just say we're going to update the time. So T will go to whatever the initial time was to that plus the time interval later. All right, so now we have new value of Q, so that if I go back to equation 1, if I put in that new value of Q at our new time, then we get an updated value of the current, and then we just iterate all of these steps over and over and over again. So for step 5 is we return to step 1 and iterate until Q reaches its maximum value. And at the same time, when Q reaches its maximum value, the current will go to 0. Okay. You may have noticed, if you've been on the course website, that last week I posted an implementation of this strategy. And so you can see the course website for an example implementation. Let me put that over there. Okay, you can implement this in many ways. The calculations are so simple. You could just do it with a pen and paper and a calculator. You could do this in Excel very easily. I'm going to show you an implementation in a Jupyter notebook. And so let me share this screen for the benefit of anyone that is on Zoom. All right, so here we go. So this is our implementation. So it starts with just some notes, and these notes just go over exactly everything that we just wrote down on the tablet here. I've chosen some values. So what did I choose? I choose 10 volts for the battery, a kilo ohm for the resistor, and 10 millifarads for the capacitor, but you can make up whatever values you like. That's not going to change any of the details. Okay, and so here are the same equations that we wrote down. So here's equation 1, here's equation 2, and that's the strategy that we wrote down exactly. Okay, and so let's see if we can see this in action. Okay, so all I'm doing in this first cell, I won't spend too much time on this. We'll go through this fairly quickly. I'm setting the voltage of the battery, the resistance, the capacitance, calculating I naught, calculating tau, and I picked the number of steps we're going to do. And so I chose 50 steps. So we're going to calculate new values of Q and T 50 times, and then we'll plot the charge as a function of time, for example. And my maximum time that I wanted was 50 seconds. And so if I take 50 seconds and 50 steps, is that what I said? 50 steps? Yeah. Then my time interval delta t, or dt here, is that 50 seconds divided by 50 steps, or it's 1 second per step. Okay, good. So that's just entering a bunch of constants. And here, we're just preparing some lists where we're going to store our values of the charge and the current and the time. And so right now, those are just all empty lists, just getting them ready. Okay, and so here is the loop. You don't have to worry about the code, but we'll just look for the parts that kind of correspond to our strategy. The first step in the loop is to use equation 1 to calculate the current. And then we're going to take our value of Q. So here we go. So here's dq. Is you calculate the current, then you multiply by the time interval. That tells you the change in the charge. And here we're updating the value of the charge. Q is equal to the original charge plus dq. And here we're updating the time. And that's all it does. It's everything that we wrote in the notes, nothing less, nothing more. So if we execute this, the thing will run for 50 iterations. And that's it. It did the calculation in a fraction of a second, okay? And so let's see. I won't go through the code here, but I'm just making plots. I'm just plotting everything that we calculated. And so we'll make those plots. There's the capacitor charge as a function of time. And it has the features that we thought it would have. Notice that like every step is the same distance or the same time. It's 1 second between each neighboring point. And you can see that initially the change in charge, the vertical steps are quite large, but then they get smaller and smaller and smaller and smaller as we go. And eventually near the end, the charge is barely changing at all. So the capacitors become fully charged. Before we look at some of the other plots, let's just think about what the time constant would be. Well, here it is. It's 10 seconds. So we chose 1,000 ohm resistor and a 10 millifarad capacitor, which is 0.01 farads. So 1,000 times 0.01 is 10. So our time constant tau is 10. And let's go look at our plot. And we can see when we wait one time constant, we get to about 60% of the total charge. So what tau tells us physically is that if you wait one time constant, your capacitor's 60% has reached 60% of its full charge. The rule of thumb is if you want your capacitor to be fully charged, you typically have to wait 3 or 4 time constants, right? So if we go out here to 40 seconds, now we've reached about, let's say 95% of the full charge. So if you're ever charging a capacitor and you know the time constant, you know you have to wait about 4 times that time constant before you get your maximum charge. Okay, let's see, what else are we going to do? We're going to plot the current as a function of time. And there it is. So initially, we start with the maximum current in our circuit, I naught. So we chose a 10-volt battery and a 1,000 ohm resistor. So 1,000, so 10 divided by 1,000 is 0.01 amps. And there it is, 0.01 amps at time t equals 0. This has the opposite effect, whereas the charge added to our capacitor started large and then got smaller so that we accumulated this kind of big charge. Here, we're losing current with each step. But in the same way, the amount of current we lose gets less and less and less as we go on in time. This is an exponential decay. So we'll write down like the exact solutions for these things in just a second. And then I think that's it. I don't think there's anything else in here to see. Yeah, that's it. So this is on the course website. If you want to play with it, you can make some adjustments. For example, this is an approximate calculation. If you want your approximation to get better and better and better, what you should do is you should shrink your time interval. Instead of doing 1 second steps, maybe we do a 1 millisecond step and we run the calculation instead of for 50 iterations, we do it for 50,000 iterations, and then your approximation will get very precise. But in fact, why don't we do something like that? The black line on this plot is the exact solution, and you can see the red dots do not follow that black line exactly. Okay, so if we make our approximation a little bit better, I bet we could get closer to that black line. So all we'll do is we'll go into here. Let's see, we have to change somewhere. Right. Let's do 5,000 steps. Okay, so we'll increase the number of steps from 50 to 5,000. And then everything else, nothing else needs to be changed. Again, it took less than a second to do that calculation. And here's the plot. And now you can see there's much more red dots. They're so dense that they're sitting right on top of one another, and it goes right through that line. Okay. So that's the sort of type of calculation that you can do very easily, very quickly, using basic computing resources. Okay, good. So I'm going to stop this share and I'm going to go back to this thing. Does anyone have any questions? Okay, good. Yeah. Yeah, so we could do that. I'm not going to ask you to do it, but I could show it to you right now. So let's do the exact solution. Okay, so if we go back to, let's see, what do I want to do? Let's go back to this equation 1, which is I is equal to I naught minus Q over tau. So I equals I naught minus Q over tau. This was equation 1. Okay, so the first thing we can do is we can say, all right, I know that I is dq divided by dt. Okay, so then we could say dq over dt is equal to I naught minus q over tau. All I'm going to do now is I'm just going to multiply through by tau. So we could say, what do I want to do? Let's do, okay, so let's do dq times tau divided by dt is I naught times tau minus q. And we'll just do a bit of rearrangement. Sorry. Maybe I shouldn't have promised to do this because I'm going to make a fool of myself, but we'll see. So instead, what I'm going to do is I'm going to say dq is equal to I naught minus q over tau times dt. So I just brought the dt from the denominator on the left to the numerator on the right. And now I'm going to divide by everything in the brackets. So this is I naught minus q over tau is equal to dt. This, you don't need to know this. This is just to show you what the actual solution looks like. And so now we'll integrate. So we'll go to the integral of dq over I naught minus q over tau. And we'll start from a charge of 0 to some final charge q. And then on the other side, we have to integrate from an initial time of 0 to some time t later. Okay. Now, you're probably far enough along in your calculus course, your integral course, that you've done substitutions. So we could think of a substitution. Let's do a substitution u is equal to I naught minus q over tau. Okay, so then when q is equal to 0, u will be equal to I naught. And when q is equal to q, u is just equal to I naught minus q over tau. Okay, so our integral equation becomes u is equal to I naught minus q over tau of, let's see, du will be minus 1 over tau dq. So that means dq is equal to minus tau du. Okay, good. So dq is going to be minus tau du divided by u. And the integral of dt is just t. So the right-hand side is easy. So this is just t. So tau is a constant. We could take it outside the integral. In fact, what I'm going to do is I'm going to divide by minus tau. And so we would have the integral of u equals I naught to I naught minus q over tau of du over u is equal to minus t over tau. Okay, what's the integral of 1 over x with respect to x? Ln. So it would be ln x. Here our variable is u, so it's ln u. So we'd have the ln of u between I naught and I naught minus q over tau is equal to minus t over tau. Okay, so then this is ln of I naught minus q over tau minus the ln of I naught equals minus t over tau. What's the ln of a minus the ln of b? Ln of a over b, right? Okay, so we can combine the two lns. So we're going to get the ln of I naught minus Q over tau divided by I naught is equal to minus T over tau. Okay, so let's see, I have I naught divided by I naught, which is just a 1. So this is 1 minus Q over tau I naught is equal to minus T over tau. Okay, so last step is to try to solve for Q. So solve for Q. Okay, so I'm going to exponentiate both sides. 1 minus Q over tau I naught is equal to e to the minus T over tau. Okay, so therefore Q over tau I naught is equal to what? It is going to be 1 minus e to the minus T over tau. And so finally, Q is equal to tau times I naught, 1 minus e to the minus T over tau. And let's just remember that tau was R times C, and I naught was delta V over R. And so this is equal to RC for tau. I naught is delta V, the battery voltage, divided by R. And so we can cancel some R's. And so finally, the result is Q is equal to C times delta V, 1 minus E to the minus T over tau. And that's the charge on the capacitor as a function of time. This line, if you plot it, would be exactly the same shape that we calculated in that Jupyter notebook. So if we were to plot this as a function of time, you would get, well, let's check it. Let's check some of these features. If I put in t equals 0, what's e to the 0? 1. So at t equals 0, we have 1 minus 1 in the brackets, which is 0. So we get 0 over here. What if we make t really large? What's e to the minus a big number? It's basically 0, right? So at large values of time, t, the exponential goes to 0. So we have 1 minus 0, which is just a 1. So a long time later, our maximum charge is going to be just C delta V. And so that's where we'll end up. And then between the two, we get that kind of smooth asymptotic approach. So this is the exact solution for charging a capacitor. And so the reason I did it the other way is because I didn't want to go through all the calculus, but there it is. We could use this result now to find the current. How would I use this result to find the current I? I is equal to what? What's the definition of current? dq dt, exactly. So we already know what Q is, so we just have to evaluate the derivative. So it's 1 minus e to the minus t over tau. All right, so let's see if we can figure it out. I have the C delta V is a constant, so we could put the C delta V out here. And then I have two terms. And so the derivative of the sum of two terms, or the difference of two terms, is just two derivatives. So I could write this as d by dt of 1 minus d by dt of e to the minus t over tau. Okay, what's the derivative of 1? 0. 1's a constant, right? So that's 0. What's the derivative of e to the minus t over tau? Yeah, so I think I heard something in here. So we'd have a minus 1 over tau, And then exponentials, when you take their derivative, you always get the exponential back again, right? So this is, you have to use chain rule to do this one. Okay, so the current, therefore, is, let's see, we have a C delta V out front. And then we have minus 1 over tau. So it ends up being a plus, and it's 1 over tau, e to the minus t over tau. So C delta V, 1 over tau. Tau is RC, right? And so the C's cancel. Then we have delta V over R, but that's exactly what we defined for I naught. And so the current is equal to I naught e to the minus t over tau. Okay, and so this is the current in our RC circuit. We could plot this as well. It would be exactly what we saw in the Jupyter notebook. At t equals 0, e to the 0 is a 1. And so you just get I naught times 1. And so at t equals 0, the current is I naught, delta V over R. At very long times, e to the minus a big number is 0. And so out here, the current is going to be 0. And then it's just an exponential decay between the two. And so you get this kind of exponential decay. And that's what the current looks like. Okay, good. So that's where I'm going to stop. What I'm going to do is I'm going to put out your midterms so that you can come pick them up. Just give me a second here. These are organized alphabetically by last name. So what we have here are A to C. So if your last name is A, B, or C, that's your file. Then we have D to I. We have J to M. Sorry. No, that's wrong. This is J to L. This is only to L. M to Q, it's over here. R to S, it's over here. And T to Z, over here. Which one?